Okay.
Okay, Judy, let me introduce you in Spanish. So sorry.
That's okay.
Okay. Para mí es un placer presentar a la profesora Judy Kennedy. Ella, muchos de nosotros la hemos tratado y la hemos conocido en congresos nacionales e internacionales. Ella, desde mi punto de vista, es una gran profesora, es una gran investigadora y pues tenemos el placer de que este día nos va a platicar un poco de su trabajo. Actualmente ella trabaja en la Universidad de Lamar en Texas. Ha trabajado ahí durante 15 años y tiene más de 80 publicaciones en artículos en artículos de investigación. Actualmente o en los últimos años ha trabajado mucho en límites inversos generalizados y me parece que esta plática tiene que ver un poquito con esa parte. Thank you so much, Judy, for accepting to give this talk. If you can start, for me, it's okay.
Okay. Well, thank you for inviting me. This is joint work that I'm going to talk about with Istok Banich, Goran Erceg, Chris Moran, and Van Nall. And we have constructed transitive homeomorphisms on both the Cantor fan and the Lelek fan. Actually, the Lelek fan came first. Yeah, we have a mission. We continue our mission of finding continua with simpler topological structures that admit transitive homeomorphisms. There are a lot of continua that do admit transitive homeomorphisms in the literature. The interval does not, of course. The interval only admits transitive mappings, but the circle does admit such a thing. Well, it's not a very interesting homeomorphism, but it is transitive. Most of the known examples of such continua have a complicated topological structure. Either they are indecomposable, such as the pseudo-arc or the canaster bucket handle, or they are not indecomposable, but they have some other complicated topological structure, such as a dense set of ramification points. Sierpinski carpet's an example, or a dense set of endpoints, such as a Lelek fan. Okay. And okay, let's skip that slide. Okay, here are the two papers I'm going to be discussing. The first one, their transitive homeomorphism on the Lelek fan, it was with Istok and Goran, and it's appeared online. All of my papers with Goran and Istok are on the archive if anybody wants to look at them. And then the second one there, which we only submitted like a week ago, is transitive homeomorphisms on the Cantor fan. And that work was with Istok, Goran, Chris Moran, and Van Nall. Okay, so some history. It's challenging to give a complete list of examples of transitive mappings or homeomorphisms that have already appeared, but here's a short list. And they're not in chronological order, okay? In 1991, I and then Peter Mintz and Bill Transu in two different papers constructed a transitive homeomorphism on the pseudo-arc, and that's, of course, hereditarily indecomposable continuum. Mintz and Transu's construction is based on inverse limits of unit intervals. Mine was factoring over an interval map. In 2022, Jerne Chinch and Piotr Oproha constructed a non-trivial family of transitive homeomorphisms on the pseudo-arc. And that generalizes the 1991 results. In 1982, Mike and Dale constructed transitive homeomorphisms on the pseudocircle. And that's again an example of a continuum that is not path connected. It is plural because one of them he constructed was a measure preserving homeomorphism on the entire plane. And the other one was also on the entire plane, but it wasn't measure preserving. Yeah, so and the pseudocircle was invariant. And on the, for the homeomorphism. So, and the homeomorphism was transitive on that. In 2019, Veronica, Jorge, and Chris Moron constructed a transitive homeomorphism on Wojcicki's universal dendrite. And that's an example of a locally connected continuum. In 2015, Jan Baronsky and Piotr Proha constructed a transitive homeomorphism on the Shapinsky carpet. And again, that's an example of a locally connected continuum. Okay, so let me start talking about the Lelek fan first and that construction. This Lelek fan transitive homeomorphism paper depends heavily on a previous paper, the Lelek fan. Let's see, I can do, this paper. The Lelek fan is the inverse limits of intervals with single value, set valued bonding functions whose graph is an arc. And there we constructed a non-trivial family of fans as behavior products. So generalized inverse limits in a sense, with closed relations on the interval. Okay, so R and rho, well, let's see. Here is the definition, but it's, I think, probably easier to just show the picture of this. If I can find it. There, okay. Yeah, the relation we're using there consists of two straight lines. One that has slope larger than 1, and so it's above the diagonal. That's the rho x, rho's greater than 1. And the other one has slope less than 1, okay? And well, not just any rho and r, any pair rho and r will work. They have to do something called the never connect, but I'll get to that later. Okay, so this pair of lines will generate when you go, we're going forward, by the way. So we're taking behavior products. That behavior product turns out to be a Lelek fan, much to our surprise. Okay, so go back. Okay. Yeah, all right. The Lelek fan was constructed by Andrew Lelek in 1960, and he wasn't the one that named it that. It got named that after the paper was written. Several characterizations of the Lelek fan were given by the Karatonics and S. Miklos in 1989, 1990. An interesting property of the Lelek fan is the fact that the set of its endpoints is a dense one-dimensional set in the continuum. That's really kind of amazing, the one-dimensional part. It's also unique. That is, it's the only non-degenerate smooth fan with a dense set of endpoints. And that was proved independently by Bula and Overstegen, and also by Karatonic in 1989, 1990. They proved that any two non-degenerate subcontinua of the Cantor fan with a dense set of endpoints are Oh, yeah, are homeomorphic. So yeah, the Lelek fan is pretty obviously a subcontinuum of the Cantor fan. It actually goes the other way too, and that we found out just recently. The Cantor fan is a subcontinuum of the Lelek fan. This fan is really kind of amazing. It seems to appear naturally in a lot of settings. But as far as we know, there were no transitive mappings constructed on it, and that's what we did. Yeah, before we could construct a transitive homeomorphism, we had to construct a transitive mapping that was not a homeomorphism. So yes, other people have obtained some interesting results on the Lelek fan or on continua with similar properties. For example, Boronsky, Mintz, and Stima showed that for any dendrite D, there is a transitive mapping on D. And dendrites are locally connected continua, while the Lelek fan is not. So the Lelek fan does not fit into this family of continua. And there are also other interesting results by Logan Hain and Chris Moran in 2014, where they got transitive mappings that are not homeomorphisms constructed on the Cantor fan. But actually, they were going for something else, I think. But a byproduct was that they had a transitive mapping on the Cantor fan. More recently, some interesting results about the Lelek fan have been attained by Hernandez Gutierrez and Logan Hain, where examples of endpoint rigid smooth fans are presented and studied. And here's here's our little picture. This is Istok drew this of the Lelek fan. Okay. And what he did was to draw the Cantor fan and then just cut off some of the little legs. Okay, definitions and notation. We're going to start with a compact metric space and let G be a subset of X cross X. X is the compact metric space. And it's a relation on X, okay? If G is in 2 to the X cross X, then we say that it's a closed relation on X. So we're going to be looking at closed relations on compact metric spaces. Okay, and then to turn that relation into an actual mapping, we're going to consider the behavior product of the G's. Okay, so that is the set of all points x1, x2, x3 in the product, infinite product of the space X with itself, such that for each positive integer, x by plus 1 is an element of G. Yeah, note that we're going in the positive direction. This is not an inverse that we're doing. Yeah, it occurred to us finally that with closed relations, they're not a function either going forward or going backwards. So why not go forward? You can always take G inverse if you want to go backward. Okay, and then so this is our space now that we're going to have a nice mapping on, and that mapping is the shift map. I don't know what that was. Okay, so sigma going from the behavior product to the behavior product is defined by, okay, sigma of x1, x2, x3, dot, dot, dot. You just lop off the first term, so you get the point x2, x3, and so forth. And that's an actual map, okay? It's continuous, but for the most part, it's not a homeomorphism. Okay, actually, it seemed to be a little bit hard to define a Lelek fan, but actually the easiest way is to define the Cantor fan, which you can say is something homeomorphic to that usual Cantor fan in the plane. And then just say that the Lelek fan is a subset of that Cantor fan, subcontinuum of that Cantor fan, if the closure of the endpoints in the subcontinuum fan is the whole subcontinuum. Okay. Interrupt me if y'all have questions, please. Are you still there? Oh, no.
Yes.
Oh, okay. During the pandemic, I'd be teaching my classes this way. And there was one time when my internet went out and I didn't realize it. So my class was gone and I kept talking for 20 minutes. Okay, so yeah, I get nervous. So if we take a dynamical system XF, so X is a space, F is the mapping, and this is an actual function now. We say that it's transitive if for all non-empty open sets U and V and X, there is a non-negative integer n such that F to the n intersect V is not empty. And you say that the map is dense orbit transitive if there is a point X in the space such that its orbit is dense in X. Okay, and it's a well-known fact that if X has no isolated points, then F is transitive if and only if it's dense orbit transitive. So you can use those terms interchangeably. Okay, some theorems, preliminary ones. If you have a dynamical system XF, and if XF, yeah, this has been known for a long time, is transitive and sigma is the shift map, then also the shift on the inverse limit space is transitive. Okay, now we're going to be talking about these two little line segments, rho X and Rx, and they're smooth and straight, so we can parameterize them as line 0 is the set of all X, rho X, such that 0 is less than or equal to, X is less than or equal to 1 over rho. And then likewise, straight line for the R. And it's easy then to kind of think about those line segments in this way, because we're going to be taking those two little functions and applying one or the other over and over again. Okay, so there's the two line segments again. All right, so for each pair R row and positive numbers cross positive numbers, we're going to define L sub R and L sub rho to be, because what I just said actually, L sub R is all the points in the square such that Y is equal to Rx. L sub rho, all the points in the square such that Y is equal to rho X. And the closed relation is the union of those two things. And then we take that closed relation and form the behavior product from that. And that is the space that turned out to be a Lelek fan. Okay, yeah, assuming R and rho never connect. And that means that, okay, R is less than 1, rho is greater than 1. And for all integers k and l, r to the k is equal to rho to the l if and only if k is equal to l is equal to 0. For a pair that does connect, a student of Istok's, Renee Grill-Rogina, has investigated that situation and actually got nice continua. I think all the continua generated by these pairs, R and rho, turn out to be either Lelek fans or another sort of interesting continuum. And Renee has investigated that. Okay. Okay, standard projection. I think that's probably pretty standard. So yes, we just take a point in the Hilbert cube and then look at its k component, and that's what Python k does. Okay, and in that original paper, we proved that if R and rho are in this never connect collection, then M's bar rho is a Lelek fan, with the top being that 0, 0, 0 point. And okay, so in that paper, we proved this little theorem. It was kind of crucial to being able to do just about everything you wanted to do, actually. So if you take a pair and they never connect, then the collection of all r to the k, rho to the l, such that k and l are non-negative integers, is thence in the positive numbers. Okay, and that's why we needed, yeah, this doesn't happen. This doesn't happen unless you've got this never connect condition. And what this theorem does is, okay, after you prove some other stuff, allow us to transition from one point to another, to a point in an open set. Take any point, any open set, there is a string of r's and rhos such that you can go from the point to that and hit something in that open set. It may, yeah, take a lot of steps, but you can do it. That was kind of one piece of why you can get a transitive mapping. And the other piece is this lemma, okay, which we have generalized now. Okay, these two ideas, this transition thing and this lemma, this is sigma transitive. We gave this a name. This it's can be generalized so that it becomes techniques for constructing transitive mappings on other spaces. But okay, what does this say? If you take a pair that never connects, oh my goodness. Okay, I'll just stop talking when it's after an hour. Is that how long I have? I guess. Are y'all still there? Oh no.
Yes,
Yes.
yes.
Oh, okay.
Yes.
Okay.
Yes.
Okay. I can't see you. Okay. All right. So we get a countable collection script U of open sets in the Hilbert cube, such that for each U in this collection, the set U intersects the behavior product. Okay. And each one of the U's is a basic open set in the Hilbert cube. And in fact, in this original lemma, had to be, the U's had to be a subset of 0, 1, not including the 0 and the 1. And then for each U in the collection, for each positive N, and all open intervals U1, U2 up to UN and 0, 1, it holds that, okay, U is this basic open set. Then there are, okay, A1, A2 up to A sub n minus 1. All of those in are either R or rho, such that, and then that got cut off, but that's on the next slide. Okay, for each U and U, okay, I already said that. Okay, there are these string of R's and rows such that for each I from 1 to n minus 1, U sub I plus 1 is A sub I times U sub I. And for each X in U intersect MR row, well, that X has associated with it this same finite sequence. Okay. And for each epsilon greater than 0 and each Z in the behavior product, well, actually, Z spy does not have to be either not 0 or not 1. It can be anything in the interval. But okay, we needed this other version first. Okay, there exists a U in U such that Z is in U in that collection, and that U is a subset of the epsilon ball around Z, and that's getting a dense set. Okay, so applying this is, okay, let me give you that. I did a picture. Okay, I don't think I need to say that. Yeah, the theorem we get from this is that M sub R rho sigma R rho is a transitive dynamical system, not a homeomorphism yet. Okay, and kind of the idea here is, okay, so I take, this is my first, so U is equal to, oh, we didn't take this off. U is equal to this countable collection of open sets. And okay, they're basic open sets. So we take the part that's not all the intervals, okay, and from U1, and then, okay, and this has the properties of that lemma. But when we get to U sub 1n, and actually what we did was build a point with a dense orbit. Okay, so we started with a point, and that point was in U11, and then automatically the next coordinate would be in U12, and the next in U13, and so forth till we got to U1n. And now we must get from the point here to this open set in the next U in the collection. Okay, and that's the transition part. And that means you pick out a finite sequence of R's and rows such that, okay, you start with an X in here, and by applying the R's and rows, so that means multiplying that X by them, you get to a point in U1. This is the transition part. And this is the sigma transitive part. Because our point's going to have its first in coordinates in U1, and then maybe a lot of coordinates later. The next, N2, I guess. But finally we get to U2, and the next N2 coordinates in U2, and then we have to transition again to U3. You do that over and over again, and that's how we build a point with a dense orbit, and that means that we have a transitive dynamical system. Okay. All right, so we don't have a homeomorphism yet. To get a homeomorphism, now we're going to take all of these spaces, behavior product spaces with their shifts, and take the inverse limit of those. And that'll turn the sigma R row into a shift that's a homeomorphism. Okay, so it turns out that this space M is also a Lelek fan. And it's going to be a homeomorphism, and it's going to be transitive. And that's how we get the transitive homeomorphism on the Lelek fan. Okay, and then now let's go to the Cantor fan. There's a picture of it that Istok drew. Okay, so we actually got homeomorphisms on the Cantor fan in 4 different ways. The first 2 we got using quotient spaces. So there, you start out with a product, your space X cross the Cantor set, and then construct homeomorphism on X cross the Cantor set. And then you take a quotient of X cross the Cantor set, okay, by just identifying that all the points that have the 1 in them as an endpoint. And of course, the mapping you built has to respect that quotient. And then you define the transitive mapping that way. Transitive mapping on X cross C gives you a transitive mapping on the Cantor fan. Okay, but I'm gonna talk about the technique where we were using closed relations. Okay, so now we're constructing dynamical systems with closed relations, and you get automatically for each one of these 2 standard dynamical systems. One is, okay, this means the behavior product. It's a new notation suggested by one of our referees, and we like it. Okay, and this is a one-sided shift. And then if you just take, instead of just X1, X2, and so forth, you go backwards too. So now X minus 4, X minus 3, X minus 2, X minus 1, X 0, X1, and so forth. And you put a decimal in there. Then you have a shift on that double-sided behavior product. And that sigma sub F there turns out to be a homeomorphism, right? And okay, and sort of, oh yeah. Okay, yeah, these 2 techniques we feel can be applied to other systems to investigate whether or not they're transitive or whether or not they have other dynamical properties. And at the very end, we gave an example to show that there's a transitive function. Oh yeah, there's a transitive function on a Cantor fan such that the inverse limit with the Cantor fan bonding vector spaces and F bonding map, that turned out to be a Lelek fan. I won't go into that. Okay, how am I doing? 34. Okay, so main theorem, there's a transitive homeomorphism on the Cantor fan. Okay, just thinking, there is a transitive function F on a Cantor fan X such that the inverse limit is a Lelek fan. Oh yeah, that's what I just said up there. And okay, I already said that. Yeah, we believe these techniques can be used to produce other homeomorphisms on other spaces to study other dynamics. Okay, so here's an easy way to define a Cantor fan. X is a Cantor fan if X is homeomorphic to the continuum. The union of all C in the Cantor set C, I guess Cantor set in the plane. What's A sub D is arc, right? Okay, so C is a subset of 0, 1. That's the Cantor set. Yeah, C is the Cantor set. And for each C, A sub C is the convex segment in the plane from 0, 0 to the point C minus 1. And okay, if you have a Cantor fan and Y is a subcontinuum of X, then a point, and call that Y, a point X and Y is an endpoint of the continuum. If for every arc A and Y that contains X, X is an endpoint of A. And the set of all endpoints of X are denoted by E of Y. The endpoints of a Cantor fan form a Cantor set, of course, and any homeomorphism on the Cantor fan is going to have to take those endpoints to the endpoints. And of course, that's true about the Lelek fan too, but the transitive mapping didn't necessarily take endpoints to endpoints. Okay, so I just copied and pasted this from one of the drafts of the paper. Okay, the Ben constructed this example. It's our fourth proof of getting a transitive homeomorphism on a Cantor fan. Okay, so the idea here are the two maps. Okay, F1 and F2. And now the space is the interval from -1 to 1. The relation is going to be the union of these two graphs. And F1 of X is minus X. F2 of X is the cube root of X for a point. Pardon? Did somebody say something?
You can continue.
Okay, okay. F2 of X is the cube root on the interval from -1 to 0, and it's X squared for X in 0 to 1. And there's a picture of the graph, okay. The behavior product of this graph, so this is Cantor fan. And it's a Cantor fan. And you get a transitive homeomorphism out of it. Okay, and to do that, well, first you take the forward limit. That gives you a transitive mapping. And then you take the double-sided limit, and that gives you a transitive homeomorphism. And it's important that the behavior product in the forward direction turns out to be homeomorphic to the two-sided one. So they're both Cantor fans, both this and this. And the shift on this Cantor fan, it turns out to be a transitive homeomorphism. Okay. Okay, and the way we did this, well, this is the actual Cole's relation that gives you a transitive homeomorphism on a Cantor fan. But we got the techniques we used were just generalizing the techniques we used in the Lelek fan paper. And yet, really, the result follows from these two lemmas. One is the sigma transitive lemma. That was that long one with the special basic open sets and so forth. And the second one was this transition lemma. And that's where we basically, this was, we have a version of the transition lemma in this too. Maybe I won't go into the details of that. But we needed both ingredients in order to prove that we had a transitive homeomorphism. Oh, and that's it. Thank you so much. Okay.
Thank you, Judy.
You're welcome. Okay, I'm stopping the screen sharing.
Is there any question?
Oh, there's Goran. No questions?
No questions.
Okay.
Okay.